Hey everyone, welcome to our video. This one is going to be on 4.5. So this is our last section to do with exponentials and logs. And this is kind of putting it just like all together. So this one's going to be all about solving them. So here's our title. 4.5 is exponential and logarithmic equations and applications, but like I've said, we don't cover very much about applications in this class in particular. So first, I'm going to give you some advice when we are solving exponentials and then when we're solving logarithmic functions. So if we are solving exponential equations, your first step is to try to get the bases to be the same. If you can get the bases to be the same, then you can just look at the exponents, which is something we did in 4.2. And we also kind of did in 4.3. If we cannot get the bases to be the same, so that's like your first option. So bases same is our first option. If they cannot be the same, if the base is 10 or e, then change to log form. So first, even if the base is 10 or e, if we can get them to have the same base, then we're good. We can use the first option. If we're not able to do that and the base is 10 or e, then we would try to just change into logarithmic form. Your third option is to introduce log to both sides. Now this is kind of a last option. It always works. However, usually we would try to do something easier than this. But if the bases are just completely different from each other, like there's no way you can get those bases the same, and then the base isn't 10 or e, then we would introduce log to both sides. And of course, I'm going to show you examples of each type of this. But before we move on to doing those examples, I'm going to talk about also solving logarithmic equations. With solving logarithmic equations, very similar to with exponentials, we have this property that we can use. If you have log on each side and the bases are the same, you can just look at what is inside the log. You can get rid of the log completely. That'll be really helpful. This rule and this idea are actually really closely connected. So if you look back at, I'm going to scroll up real quick, at the last example we did in our last video, the reason I can introduce log to both sides is because I'm using this rule right here, but I'm just using it backwards. Like I'm going from this to this version of it. And that ends up being a method for solving exponentials. Going this way with it, from this way to this way, is a method for solving logarithms. Now, if this is not possible, then you can move to exponential form. So first you want to try the first one, and then if that doesn't work, like it's not possible, and I'll show you, of course, somewhere it's not, we'll then just move to exponential form. That'll be our only option. For both of these, we may need to combine some logs first. So that would be using properties from our last section, 4.4. So we may need to combine some logs together before we can see this rule happen, or maybe before we can move into exponential form. So we'll see that. But for now, let's go ahead and jump into some problems. So these are just going to say solve, and I have a bunch of them for us. So the first one we're going to start off with is 2 to the negative x equals 1 over 8. Next, we'll do 3 to the 2x minus 6 equals 81. C, we do 25 to the 4 minus t is equal to 1 over 5 to 3t minus 1. And I have one more as well, but I don't want to run out of space. So for example 1, all of these actually have the same base, meaning on each side I can get the bases to look the same. So 2 to the negative x, and then 1 over 8 can be written as 2 to the negative 3. So I can use that rule, just look at the exponents. So I get x equals 3. Now that I've done one, you should try to do some yourself. So pause my video and try to do some alone. I always say whenever you're trying problems, at least just try to think like, if this was on a test, what would I try to write to get partial credit? Like, can I write anything for this problem? If you don't even know where to start, that's definitely a problem. Now 3 and 81, I can make those bases the same. So 3, I can leave. And then 81, I can write as 3 to the 4th. So now that my bases are the same, I have 2x minus 6 equals 4. And I can just solve this like a regular equation. So add 6. So this gives me 2x equals 10. Divide by 2. So x equals 5. For part C, I can see that 25 and 1 over 5, I can write them both with a base of 5. So 25 I can write as 5 squared, and then I'm leaving the top there. Now 1 over 5 I can write as 5 to the negative 1, and again I'm leaving the rest alone. Now when you have exponents separated by parentheses like that, You multiply them. So when we write this as a new equation, now that my bases are the same, I can just look at the exponents. I get 2 times 4 minus t is equal to negative 1 times 3t minus 1. And I at least think you should be able to solve from here. So for sure, go ahead and pause and try to finish this one out. First, I'll distribute, so I get 8 minus 2t equals negative 3t plus 1. I will combine like terms. So if I add 2t and I'll subtract 1, I get 7 equals negative t. So t equals negative 7. So that one was a little longer. I have one more for us. And this one's actually similar to one I did in, I think that was 4.2. 4 to the negative x plus 1 is equal to 32 to the 2x. I did a problem with 4 and 32. And the hard part about this one is that the base isn't as obvious. So in all the other ones, the base you need to get to is like already written, right? So like for A, 2 is my base. 3 is my base for B. 5 is my base for C. For this one, you might want to try 4, but you can't do 4 to the anything to get 32. Not easily, at least. What we do instead is 4 can be written as 2 squared. And then I still have the negative x plus 1. And then 32 can be written as 2 to the 5th. And I still have this 2x here. So sometimes the base might be a little harder to figure out. Now I'm just going to look at the exponents. So I get 2 times negative x plus 1 is equal to 5 times 2x. And I will go ahead and distribute and everything. So this is negative 2x plus 2 equals 10x. Combine like terms, I get 2 equals 12x. So x equals 2 over 12. So x equals 1 over 6, fully simplified. So those are some examples of getting the base to be the same. Now let's look at some where maybe my base is 10 or e, so we can practice just moving into the log form. So example 2, I'm still just going to say solve. So this one says 10 to the power of x equals 50. And then b, I have 2e to the 0.5x is equal to 6. So right, I can't get my bases to be the same because I can't get 10 and 50 to have the same base. With b, my base is e on one side and 6 on the other. I can't do anything with this. But because it has a base of 10 or e, we can just move to logarithmic form. So for log form, my base is 10, so I'd have log. Remember that logs are equal to exponents, so it's equal to x. And then the 50 was by itself, but now we're in log form, so it's going to be in the log. And this is it. We can leave it like this because it can be approximated by your calculator. Now remember that on the test, I do not require you guys to use a calculator, so you can actually leave your answer like this, and that's fine. For part B, I'm not really able to immediately go into log form. I see the base of e, so I want to, but I don't know what to do with that 2. Remember that this is just multiplied, so I can divide out that 2 first, and I get e to the 0.5x equals 3. Then I'll move into log form. Because my base is e, I need to use ln. Logs are equal to exponents, so it'll be 0.5x on the other side. To get x alone, I'll divide by the 0.5. So I get x equals ln 3 divided by 0.5. And we can just leave that. Or you can approximate it in your calculator, but I'm fine with leaving. Again, I said this for the last section. I really don't think that the homework sections are long enough for these. I really do think you should try some from the book just to get more practice. I mean, you can just look up problems, you know. You can ask ChatGPT to give you problems, you know. Give me exponentials and logarithms to solve, equations to solve, you know, and just get any new problems you can look at. Khan Academy is a great resource. I really do recommend trying to practice more of these and to see them randomly. For our last type of example with exponentials, we're going to do some where the bases are just way different from each other. Can't solve them. Like, can't get them the same. And if the base is weird, you don't want to move to just exponential form or logarithmic form, because then you still can't, like, approximate it. The only way you can leave log in your final answer for solving problems is if it's a base of 10 or e. That's the only way to be considered fully simplified. So for our first one, we're going to do 6x equals 7 to the power of x minus 1. And of course, we'll do another one. We'll do 3 to the power of 2x minus 1 equals 5 to the power of x. So this one uses a really similar idea to what I left off with in the last video we did, where we introduce log to both sides. The reason we want to do this is because if we can introduce log to both sides, be careful, that's a whole exponent on that 7, not just the x. The whole reasoning for this is that log, we get to use a certain rule that we basically get to exploit. When we introduce log to both sides, remember, I keep zooming in on accident. Remember that exponents can move out to the front for logarithms. They can turn into multiplication. So this is a great way to get our variable out of the exponent. So I'm going to rewrite this as x log 6 equals x minus 1, keep that in parentheses, log 7. Because it's the whole thing multiplied by log 7. Now I can distribute this side. So I'm going to distribute because I want to get the x's on one side, but right now that x is trapped inside the parentheses. So I've got to distribute. Now, like I said, we're trying to get our x's on one side because that's how we solve for a variable. We get it on one side. So I'm going to move this x log 7 onto the other side. So I get x log 6 minus x log 7 equals negative log 7. Now this part's a little unique. We did this in 4.1, but if both of these have an x, that's a greatest common factor. So we can pull that out to the front, factor it out, and we'd be left with log 6 minus log 7. And so now this is x times all of that, so we can divide it out. So my final answer here, I get x equals negative log 7 divided by log 6 minus log 7. Now technically this final answer can simplify just a little bit more. Remember that, okay, 1, do not cancel. That's impossible. Don't do that. But remember that if you have logs subtracted, they can turn into division if you write them as one log. So this is negative log 7 divided by log 6 divided by 7. And I'll go ahead and box that in. That is fully simplified. So that one was a little bit long of a problem. Now, of course, I really do recommend, since I just did one, you should do the next one by yourself and just kind of see where you get stuck. But I'll go ahead and do it. So my bases are totally different. So I'm introducing log. Then I'll move my exponents to the front. Now I need to get my x's on the same side, but right now I have one of them stuck in that 2x minus 1. So I'll distribute to be able to get it out of there. Now I'm going to move all my x's onto one side and anything else on the other side. You can decide how you want to do this, but I'm going to move mine like this. I'm going to move my x log 5 onto the left, and I'm going to add my log 3 onto the other side. So all I did here was I moved things around a little bit from side to side. Now that my x's are on one side, I can factor them out. And then I'll divide by the leftover. So I'm dividing by this whole thing. So I'm just going to rewrite that answer. Now this can simplify a little bit further. Two log 3 is the same as log 3 squared, which is 9. And then at the bottom, if you're subtracting logs, you can write that as 1 log with division. So 9 over 5. So this is fully simplified. That's definitely your longest type of problem that you could see. All right. Now let's look at solving some logarithmic functions. So example 4, I believe, yeah. Example 4, we're going to do some logarithmic ones. So we'll say solve, and let's do ln x squared equals ln 3x. Now, something else that I need to mention with logarithmic functions, equations, you need to check for extraneous answers. The reason is, remember when we did square roots, and it's because square roots have certain numbers you don't want to plug in that sometimes we ended up with extraneous answers. Well, logarithms are the same way. They have domain restrictions, right? So there may be numbers that we get that if we plug it back in, we actually get something like undefined or like an error or something. So we're going to have to be careful that we check our answers. So we will need to check answers for logarithms. So for our first one, I see that I have log on both sides, so I can actually just get rid of it and only look at the insides. X squared equals 3x. Now you might be tempted to divide by x, but something I've told y'all when we did quadratics, right, because x squared, this is a quadratic, don't do that. You can't divide by a variable. You can move everything to one side and you can factor out a variable, but you do not ever want to actually divide by a variable. What this gives me is x equals 0 and x minus 3 equals 0, which is x equals 3. Now this one, there's an issue with one of these. If you plug 0 into the original problem, remember that the inside parentheses of a log can never be 0 and it can never be negative. It should always be bigger than 0. So this is an extraneous answer. So our answer for this one is just going to be x equals 3. Let's do another one. This one says log x minus 4 equals log x plus 6 minus log x. Now for this one, I see that everything is written in log, which is great. That means I'll probably be able to use that property where I have like log equals log of stuff. But I need it to just be like 1 log equals 1 log. So on my right side over there, I'm going to need to combine those logs together so that I only have 1 log on each side. So this would be log x minus 4. Combining the logs on the right, I get log x plus 6 over x. Now I can use that property and ignore the logs and just look at the parentheses. So it'll be x minus 4 equals x plus 6 over x. And now I just solve this like normal. So anytime I have denominators, I multiply by them to get rid of them. Be careful though, you need some parentheses. So this becomes x squared minus 4x equals x plus 6. The minute that you see an x squared, you're probably dealing with a quadratic, so we should move everything to one side and try to factor. So this will be x squared. If I subtract x from both sides, subtract 6 from both sides, I get minus 5x minus 6 equals 0. Then we can factor. Now you're not guaranteed to be able to factor these. You could have to use quadratic formula or something like that. But this one does factor into x minus 6, x plus 1. So I get x minus 6 equals 0, which is x equals 6, and x plus 1 equals 0, which is x equals negative 1. But be careful. If you plug in negative 1, you're going to get some errors because the inside of the parentheses of a log should never be negative. So this is an extraneous answer. So we don't want to box that one in. We only want to box in x equals 6. That's my only good answer. So we want to always watch out for that. Now let's do some where maybe we can't use that property and we have to just move to exponential form. So C, or I was going to make a new example. This is example 5. Again, still saying just solve though. But the first one, I have 4 log base 3, 2t minus 7 equals 8. And I guess I'll write the other one on there. Part B, log base 2 of x equals 3 minus log base 2 x minus 2. The kind of red flag on both of these is that you have a number outside of the log. If you have a number outside of log, you're going to have to just try to move into exponential form. Now you may need to do some work first to be able to move to exponential form, but that's going to be the ultimate goal. So for part A, I don't know how to change into logarithmic form with that 4 sitting there, so I can divide out that 4 first. Always check if there's anything you can do there. So this becomes log base 3, 2t minus 7 equals 2. And now I'm going to move to exponential form because that's the only way I can get this t out of those parentheses. So my base is 3. Logs are equal to exponents, so my exponent is 2. And then the 2t minus 7 is now out of the log. Simplify, so I get 9 equals 2t minus 7 Add 7 to both sides. So that'll give me 16 equals 2t. Divide by 2. So t equals 8. And you can always plug it back in to check it. For my next one, but as long as we don't get like a domain error, it's probably fine. And then for this one, again, I have multiple logs happening, but I have a number outside of the log. So that tells me I need to move to exponential form, but before I can do that, I need to combine these logs into one. So my first step here is I'm going to add this log to the other side. That way I can put them together. And then I'll be able to move in exponential form. So putting my left side together, and at this point, go do it yourself. You can do it. But putting them together, didn't mean to zoom in. You get log base 2. They're separated by addition, so this is multiplication. In exponential form, because now I have my log by itself, I would have 2 cubed equals x times x minus 2. I'm going to distribute and simplify, so I get 8 equals x squared minus 2x. Anytime you see an x squared, you probably want to try to factor. So I'm going to move everything to one side. This does indeed factor into x minus 4, x plus 2. So my answers here I get are x equals 4 and x equals negative 2. But I can't plug in negative 2 because it's going to give me errors. So that is an extraneous answer. Only x equals 4 is the good one. Now I have one more type of problem that I wanted to show you, and this one is like it, it kind of brings back some stuff from 1.6, actually. I know it's been a long time since we did that. I'm pretty sure 1.6. It was the one where we just did like a bunch of different types of solving, and we did one with factoring using a substitution method. So I saw this one come up, and I was like, oh, I should probably do that. So solve. This one says e to the 2x plus 5e to the x minus 36 equals 0. So this is a little bit of a unique problem. And the point is it should kind of look like a quadratic to you, except the e is like throwing it off. So if we were able to replace this e, so if we let u equal e to the x, we could rewrite this as u squared plus 5u minus 36 equals 0. Let me write it like this first as well. Maybe this would help. Hold on. I'm trying to erase, but it's always like so slow. Oh my gosh. Erase. There we go. This is the same thing as seeing e to the x squared plus 5 times e to the x minus 36 equals 0. So I'm just replacing the e to the x with u. I thought maybe just me writing it as u squared might look a little weird, so I wanted to rewrite it. Now this we can factor. Two numbers that multiply to get 36 but would add to get 5 would be 9 and 4. So this would be u plus 9, u minus 4. So I get u equals negative 9 and u equals 4. But be careful, I don't want u, right? I want x. So I have to plug it back in to this. So I have negative 9 equals e to the x, and I have 4 equals e to the x. To solve these, I have to use ln. I got to move to exponential, logarithmic form. Because I can't get my bases to be the same, right? Because e and negative 9 can't get them to be the same. But since the base is e, I can move to logarithmic. So in log form, I would have ln, my base is e, and it's equal to the exponent, so my negative 9 would go in here. Now be careful with this. This is not allowed. Ln of a negative number is not allowed. So extraneous, not a good answer. Don't box that in. Very bad. But the other one is good. So ln base of e into logarithmic form. Now you don't have to write the e on there, so you can just write ln of 4. So that is the answer to this problem. So anyway, I think I remember seeing something similar maybe on the homework or something like that, but I was like, oh, that's kind of nice. I like how it brings in like an older topic that we did while also contributing to a newer topic. So we've done a lot of solving in this video. So you could see just, any of this on the test. So that's why I say whenever you're doing the homework, it's probably not enough. Just the homework, just the online homework. So you want to look through the textbook just so you can get more problems. Of course, the sections are probably going to go over things that we did not. So if you look a lot into the textbook, you're going to see applications and stuff. And we didn't necessarily get into that. But at least for more example problems, it'd be a good place to look. So as always, if you have questions, please reach out to me. But otherwise, I hope you'll have a wonderful day. And I'll see y'all in the next video when we start chapter 5. Bye-bye.